So before Serge starts, Serge is a professor at EPFL in Switzerland. I know Serge for many years. Anybody who has done research in cryptography must know Serge, and if you don't know it, now it's the time to know him. He has been working in cryptographic community for many years, doing research on various topics, and now he's also focusing in part of his research on contact tracing. So Serge, uh, the stage is yours.
Okay, thank you very much. Thank you for the invitation to speak here. So I'm Serge Vaudenay. I'm going to talk about SwissCovid, which is a Swiss app. And it's the app about digital contact tracing. And I'm from EPFL, and probably you know that EPFL was the leading house for the development of SwissCovid. So I have to say that everything in this talk does not reflect the viewpoint of my employer. So thoughts are totally mine. When I try to illustrate the viewpoint of EPFL, so I actually found a nice image, which is a painting from a German painter illustrating how EPFL gave SwissCovid to humanity. So, of course, it was about Prometheus giving fire to humans. And we hope that the story will not be the same for EPFL. So, SwissCovid is a decentralized contact tracing app. How it works, so we have participants. Those participants, they have smartphones, and with their smartphones they send all the time some random numbers over Bluetooth, and those random numbers are visible by their neighbors. So here we have 3 participants. So when they select some random numbers to send, they also keep record of the numbers that they sent. And when they receive some random numbers, they also keep a list of all the numbers they have received. If one participant gets sick, he goes to the hospital, he gets a test, and unfortunately it's positive. So when it's positive, it receives an access code, which is a one-time access code, which has a limited validity duration. And with this access code, this user can upload all the keys which have been used in a recent past, so that everybody can see on this public server, which is a bulletin board, all the keys which have been used in the past. So for this guy, he will see the key, it will not match any of the received keys, so he will just ignore. But for this guy, he will recognize that this key has been seen before, and it will raise an alert. So that's the principles of the decentralized contact tracing. SwissCovid was developed in a DP3T project, which started on April 1st at EPFL. And DP3T stands for Decentralized Privacy Preserving Proximity Tracing. So you know that when there are titles like this with something like an adjective in the title, so you may wonder if it is correct or if it is a smoke screen. So for me, this privacy preserving in the title is a smoke screen because it's not privacy preserving at all. So this application requires all users to have Bluetooth turned on. And not even that it is on, it's also sending all the time. So it's sending 4 times per second some random numbers, which repeats during 10 to 15 minutes. And after that, it changed to another random number. So it means that if you have some sensors, some Bluetooth sensors, which are spread all over a building, in the street, etc., you can follow the movement of users. You can really track them. So that's an attack which is feasible. You can trace all users of SwissCovid, but it requires an infrastructure of Bluetooth sensors. If you don't have such dense network of Bluetooth sensor, you can still have an attack, but only for reporting users because they are easily recognizable. So here, this is a picture that I took from a paper by Ahmad. So I think that he's going to talk about it later. So that's a picture of Darmstadt, where there are a few sensors which are spread over the city, and you can recognize the movement of some user who later was diagnosed. So you can see that this app is not privacy preserving also its name as such. We can wonder how it got successful, and the success was based on some early uh, notice that this type of technology will be hard to deploy because of the access to the Bluetooth interface on the smartphones. This access to the Bluetooth interface is controlled by the operating system and therefore by Apple and Google. And at the very beginning, Apple and Google say that they would favor decentralized apps, and this is how this decentralized technology became successful. So here I found a picture of DP3T meeting Apple and Google and agreeing to have the deployment of this technology. The problem with this story is that DP3T at the beginning, they saw that they would get access to the Bluetooth interface in a smartphone, and they will be able to beam whatever they want and to scan however they want. But it didn't work this way. So instead of getting access to the Bluetooth interface, Apple and Google decided to implement the protocol. And they didn't give access to the Bluetooth interface, but to their implementation, which is the Google and Apple exposure notifications that Ahmad talked about, again, which is in smartphones. So this is how the story began, and this technology becomes successful and deployed in many countries. At the beginning, DP3T wanted to have something which was open source, fully open source. And this message was taken by the parliament, who decided on the legal basis of SwissCovid. So the parliament has to adapt the law on epidemic. So it was done on June 20 this year. They added a new article which defines the legal basis of SwissCovid. In this article, in alinea 5E, it is said that the source code must be public for all the components of the system. And you may wonder how possible, because GAN has no open source code, and nevertheless it is deployed. So it is a problem. It is a problem how to deploy with such a law. It's even worse than this, because it's written that the source code must be available. It must be also verifiable. So people should be able to verify that the source code which is provided is the one which is implemented on their smartphone. And that's for all components. It's explicitly mentioned for all components. The law also says that the government is in charge of the details. So of course, GAN is not compliant to this requirement. So it becomes a problem of the government. So the government has to solve the problem. And since it is in charge of the details, he published an ordinance which kind of solves the problem. In this ordinance, which was published 4 days after the law on epidemics, the revision on the law of epidemics, so it means that it was in preparation even before, when it was still under discussion at the parliament. So this ordinance, to solve the problem, defines what are the components. So we say that all components must have a source code available. GAN doesn't have such. So let's define what are the components. And in these components, there is an exhaustive list of what are the components of the system. And in this list, there is no GAN. GAN appears in another part of this ordinance, Article 5. Article 5 defines all the tasks that SwissCovid app must complete. And it describes all the tasks. And in all the tasks, like selection of a daily key, exchange over Bluetooth, storage of received keys, etc., those tasks can be done with the help of an interface of the operating system. So this is where GAN appears. GAN appears as a helper for the app. So it's not a component, but it's a helper. But instead of helping, it does everything. So all the tasks, nearly all the tasks are outsourced to this helper. The app doesn't do anything which is in black here. So the app takes care about downloading the keys to the bulletin board and notifying the user, but that's it. All the rest is done by GAN. So GAN is not a component because we define explicitly what are the components. GAN helps the app, and explicitly it's mentioned that this part of the operating system is not required to have a public source code. So it's implicit that GAN is not a component, and it's explicit that it's not required to have a source code. So the problem is solved, and we can deploy SwissCovid. So this is how it happened. So you can think whatever they want, but for me, it's a government cheating with the law. Next problem is still about the legal basis. The ordinance says that the proximities to be considered are the proximities at the distance of 1.5 meters. So if we strictly interpret this, it means that if you are at a distance larger than 1.5 meter, it shouldn't be taken into account. And if you're lower than 1.5 meter, it must be taken into account. Problem is that, as Ahmad said, Bluetooth is not made to measure distances, and this measurement is not reliable at all. So right after the release of this ordinance, Lace and Farrell published a report where they have shown that in a real life experiment, so it was done in a tram, this kind of technology is not able to measure reliably if the distance is lower than 1.5 meter at all. The decision to decide if it is lower is not better than random. So it means that whatever is received, it's randomly decided that it's close enough. And this result match more or less the experiments which were done by the designers of SwissCovid, where they have shown that when the actual distance is 1.5 meter, the probability that this application will consider that it's close enough is 57%. And when the actual distance is 3 meters, the probability that it thinks it's close enough, it's 45%. So you see that the difference is not so big. So we can see that the correlation with the actual distance is very weak. So the distance measurement is not precise, and the time measurements is not precise either. This ordinance says that contacts which last 15 minutes must be taken into account, and that's a total of 15 minutes. It works well if people are not moving, but if people are moving, it's not precise at all. So when you send a Bluetooth beacon, it's done continuously. The beacons is repeated 4 times per second, so it's almost continuous. But when you listen to Bluetooth, it's not continuous at all. So GAN actually scans Bluetooth nearly every 4 minutes. So it scans for a few seconds, and then it sleeps for about 4 minutes, and then it scans again. So it means that if something happens in between 2 scans, it's not visible by GAN at all. So in a situation where people are moving, we can wonder what is the probability that GAN will notice a total duration of 15 minutes. So I did the computation. I consider a party where people are moving, and the party lasts for a duration which tends towards infinity. And we have a proximity between 2 people, which is lambda times 4 minutes. And we wonder what is the probability that it will be considered as something which is more than 15 minutes. For this, we need 4 scans. So we need to be observed during 4 scans. And the number of scans follows a Poisson distribution. And if you plot the probability to have at least 4 scans, so when you have a contact of duration 15 minutes, the probability to have 4 scans is 52%. So it means that you have nearly a 50-50 probability to be spotted when people are moving if your contact is 15 minutes long. So the measurement of time is not precise. And time also appears in a weird way when we consider time traveling. So probably you remember this movie, which is from 1985, Back to the Future, where a time machine was made, and one hard instruction of this machine was never to set it to 2020. So at this time, maybe we didn't understand. Maybe today we understand better why this rule was in practice. And because of that, we wonder what would be the impact of time machine on the security of SwissCovid. And this is what pushed us to publish this paper, where we analyze what is the role of time traveling in the security. So it's available on ePrint. And we design an attack which is really effective. So how does it work? So you have an adversary here, and we assume that this adversary is able to make victims move, travel through time. So this adversary will wait until someone published a code on the bulletin board. The adversary doesn't need to know who is this person, it just needs to see one new key posted on a bulletin board. And when he retrieves this key on the bulletin board, he will check at what date this key was used, and it will send the victim back to this date. He will just replay this key and then wait until the victim comes back to present and download the key, and then realize that he may be at risk to be infective because he has met the person who posted this key. So it is a very simple attack. Problem is that we need a time travel machine. So to make people travel through time, it's a bit technical, so we don't really know how to do. But to make smartphones travel through time, it's something which is very easy. One thing we can do is to have physical access to the smartphone of a victim and to change a date. Or we can try some intrusion attack to try to log in the smartphone and change the clock. So it's an intrusion, of course, and we can also do it without intrusion. So something that we did, so that's what was on a previous picture, is that we can use a Raspberry Pi. As this Raspberry Pi connect to the Wi-Fi, it can use Bluetooth as well. And if we assume that the victim and this Raspberry Pi are connected on the same Wi-Fi network, they have access to the internet using the same Wi-Fi, this device can do some ARP spoofing attack on the NTP messages and change the NTP messages which are received by the victim so that the victim will believe that it is at another time. So we can make like this, the victim travels through time. The problem is that it depends on what are the priorities for the time definition on the smartphone of the victim, and the NTP time may have a lower priority. It has a high priority when the victim doesn't have access to the data network. But if it has access, then we have to consider another time machine. So for that, we need to use a rogue base station. So that's a rogue base station that we have used. And like this, we can simulate the network and send some wrong time information to the victim. It's something which works efficiently. Like this, we can make the clock of a smartphone change in 100 milliseconds. So we need 100 milliseconds to change the clock of a smartphone. We can also consider the GPS signal, but it's a bit more technical, and usually it has a much lower priority, so we didn't really consider it. So how our attack works, so we need to wait until one key on the server is published. Then we send the victim to the time where this key was used. So when the victim arrives to this time, the smartphone realizes that it didn't scan for a while because it didn't scan before. So it triggers immediately a scan. So if we replay the key, then it will be one scan. And then either we wait for a few minutes, and if we are impatient, we can use our time machine to make the victim travel 5 minutes ahead. 5 minutes ahead, it will realize that it didn't scan before, so it will scan immediately. So we'll have a second scan, and we do a third one like in the same way. And like this, it will be considered as 3 scans of 5 minutes, so 15 minutes, and that's enough. We just have to wait until the clock is reset to the present time. It downloads a key, so it can take a few hours. because normally smartphone check the server every 4 hours. And like this, the victim will receive a false alert. So the total duration of the attack is 1 second this way. So we can run our attack in 1 second, and with an amplifier, we can do it massively over a radius of 500 meters. With a better equipment, we can push the radius to several kilometers. So we didn't try to do it massively, of course. So we run the attack in a Faraday cage, and it works very well. So here is the screen capture of an alert on SwissCovid. So this is a message that a SwissCovid user receives when he has an alert. And it works also on Immuni, which is the Italian app, on Coronavarn, the German app, on Corona Alert, the Belgium app. It works also on the British app, NHS COVID-19. So that's the message that people receive when there is an alert. And it also indicates that they should self-isolate for a few days. And we were wondering what would happen after this number of days, and we didn't want to wait for that. So we use our time machine to move ahead 11 days, and then we receive this message. So that's what we can do. So it's very easy. We don't need to corrupt the victims, the health infrastructure, or whatever. So the attack is very easy to do, and it doesn't require huge equipment. Anybody can run this attack. So, and those attacks, they are not surprising at all. So they were known, they were identified, and people knew about it, but they were always downplayed. So here, it's one of my favorite movie where there is one character, which is a DP3T designer here, who tries to convince innocent user that SwissCovid is privacy preserving, that it's secure. It says, oh, there are some attacks, but they are too expensive, they are not practical. And actually, it illustrates the situation where SwissCovid was declared as being privacy preserving and secure.
Excuse me, 5 minutes left.
Okay, so we can wonder how about the adoption? So in the adoption, we can check that roughly 22% of the population in Switzerland is using SwissCovid actively. We can wonder what are the reasons for others not to use. And for that, there was a survey by Fonville who says that 37 of people who do not use perceive that there is a lack of usefulness of the app. As a matter of fact, so this app is only useful if you're about to meet stranger and to stay close to them. Like, for instance, if you take public transport or you go to restaurants, but otherwise it's mostly useless. For 23%, it's because they don't have the proper equipment. So for this to work, you need a smartphone which is running iOS or Android. It should not be too old. It should not be too recent either and Chinese, because the US doesn't want a Chinese phone to use American technology. So it doesn't work on Chinese recent phone, and it doesn't work on Android phones which have been de-Googled. It's still using Android, but it doesn't work. For 22%, there are concerns about privacy, and there are various other problems. We can wonder how many contacts are in the system. So that's a curve of the number of cases that we had in Switzerland. It's for a period of 7 days. So that's the second wave. So it started this summer here. So that's the second wave. And that's the curve of the number of people who entered a code into SwissCovid to report. The ratio is something which is more or less stable between 10 and 20%. It's roughly 15%. So it's something which is a constant ratio. We can wonder what is a real contribution. So there is another survey by Fonville, which was done in a state of Zurich. It's about 1 million people, where they had a period with 1,700 cases in total. So this is the number of app users among those cases, and this is the number of people who reported using SwissCovid. It's, you can see 20%. It's correspond to the ratio we had before. we can wonder how many people were alerted by these people. So the number of people who receive an alert was estimated to 1,400. 1,400 receive an alert. And out of those 1,400, some called the info line. So they were put in quarantine by the info line. 166 were put in quarantine. Some were suggested to have a test. And out of those who got a test, 30 were positive. So you can see that only 2% of people who are alerted become some positive cases. And these 30% of cases, it corresponds to 1.75% of the entire cases. This number 30, it's used by promoters of SwissCovid to claim that SwissCovid is useful because it kind of discovered cases. Of course, it's a quick argument because this only says that those people were alerted, they got a test because they were alerted, and it was positive, but probably they suspected they were under risk because they were alerted by a close contact, and probably they were already in quarantine. That we don't know. So we don't know if these 30 cases were really discovered by SwissCovid. We can also measure compare the 160 quarantines with the total number of quarantine in the canton. It's 5%. So you can see that SwissCovid contributes up to 1.575% of discovering the cases and contribute to 5% of quarantines. So it's not so effective. So in my opinion, SwissCovid is not so effective. I doubt that it has any significant role in fighting against the pandemic, and probably there are some better measures. So this is one of my favorite measures. People at the beginning, they thought that garlic would defeat COVID-19. Against the disease, it does nothing at all. But if you eat garlic, you can be sure that people will stay away from you. So there will be no one at a distance of 1.5 meters. So it's an effective measure. So to conclude, so this is a picture from a show by Shakespeare, Much Ado About Nothing, where people praise SwissCovid. In my opinion, SwissCovid make many promises. So they promise that it would be privacy preserving and secure, also it's not. Instead, they strengthen the monopoly of Apple and Google in this technology. So now there is a unique technology, which is the one by Apple and Google, and it makes the government cheat with the law to be able to deploy it. Probably this technology is mostly useless. And that's more or less what I have to say about SwissCovid. So I put more in this URL if you're interested. So thank you very much for your attention.
So thank you, Serge, for the nice talk, nice pictures. So, so any question from the virtual audience or real virtual?
One question from Mr. Greenbaum. Maybe you can unmute yourself and
yes.
Go forward.
Thank you, Liza. Many thanks for the talk. Indeed, these numbers are very clear, and we've learned a lot from a series of papers about the Swiss app. But the stats you were showing about the Zurich case don't seem to depend on the use of centralized Dogain protocol. I would expect them to be true for any app that uses BLE, Bluetooth Low Energy, more or less anywhere. Will it confirm that? What do you think?
Yes, so it's totally independent. So here, that's the numbers that we obtain for a system which has maybe 22% of the population using it.
Thank you.
So any other question? Thank you.
Yeah, Mr. Esching, you can ask your question. Please unmute yourself. There's no microphone. Okay. So I will read it. Regarding the time travel attack, wouldn't almost everything break in a smartphone if that was possible, like TLS, etc.?
So I think that the problem of the reliability of time is a regular concern in security conferences. So I don't have in mind other problems, but probably with the validity of certificates or etc. there are concerns. Here maybe something which is interesting to know with respect to the previous question is that this attack, it really works in the GAIN infrastructure, and it's based on the fact that we can have the keys on the public server and replace them. But otherwise, this playing with time, it has also many other consequences in other domains.
So I think if there are not urgent questions,
We
then,
have another one from Stephen Farrell. Maybe Stephen,
please, Stephen Farrell, definitely.
can unmute yourself, or I will read it again.
Yeah, no, sure. I can unmute. I don't know if it works, but I'll try. I'm just wondering, do we know if anybody's been trying any of these replay-based attacks, or even if there's anybody trying to look and see are there replays happening?
I don't know about other people who try. So we try the replay attack based on our time machine. And I don't know if other people tried it, but in my opinion, it works with no surprise. It's a matter of time to develop.
Yeah, no. I don't mean researchers. I mean, is anybody actually trying to mount the attack?
If this attack happened in the malicious attack, I don't know, and probably there is no way to know. So it's very hard to know.
So,
it has been always claimed by authorities that they can live with this risk. Say they don't really care.
So I
say that attacks would be too complicated to run, essentially.
So
yeah,
I see another hand raise from Paul Francis. So maybe we can say it's the last question.
We go for Paul. Hello, Paul. Thanks for attending. Okay, please go on. And then afterwards, we go to the next speaker.
Yeah, it's a little bit to the question somebody else just typed in. There are plans for improvements, or Serge, if you have any ideas how to overcome some of these problems, such as low pickup rate, or lack of effectiveness, or anything like that. What can be done? I
don't think there is any plan to fix those privacy and security issues. So these privacy and security issues were known since April, and since then
No. I'm not talking about the security issues. I tend to agree with the government that these are not serious. I mean, getting a more effective app, more uptake, better track.
Okay, so yes, so regularly, so there are concerns that not enough people are using it. So 22% for me, it's a huge number already. I don't think it's realistic to believe that more will really use it. There are plans to try to make more people use it. I don't know if it will work.
Okay, so
answer the question.
So maybe we just need to move on.
Thank you.
Thanks a lot, Serge, for your talk. And maybe one comment from my side to Stephen's question. There are attacks running, but as you may know, these attacks are on public health system, and these are illegal. So that's what I can say. And what I say is not what TU Darmstadt says. It is my own knowledge. So you can be sure that there are attacks running. But if we are going to publish any attack as researchers, we may have some problems with government, because government is behind it and the lobbyists are pushing for that. Anyway,